Well, everything can say a lot about Jean-Christophe, and it's an honor to be here. Okay, so let's start with the setting. The setting is pretty clear. We are going to consider smooth maps on a manifold. This manifold is going to be, could be open, could be compact, doesn't matter. Smoothness means at least C1 plus alpha. And the focus will be to try to understand the system with zero entropy. Well, we know the notion of entropy, and we want to understand then. A typical example of zero entropy map is a Morse's mail, an irrational rotation. And the goal is to characterize this one that have zero entropy. So it's possible to say a lot about which one have zero entropy, and in particular to try to understand the interior of the system that have zero entropy and the boundary. There is only one result in a lot of generality that is already known, which only holds in the C1 topology. It's only known in the C1 topology, which basically say that the interior of the closure of zero entropy, and this is in the C1 topology, coincide with the interior of the closure of Morse's mail. But this previous result does not say much about the boundary. So we want to say what is going on the boundary. On the other hand, it's neither say a lot about which is the mechanisms that bring a system that zero entropy to one that has positive entropy. If it's possible to say something about these mechanisms. And moreover, it's only known in lower topologies. So there are these three problems that we would like to address. And of course, in general, not much is known. And let's start with a very well-known scenario, which is one-dimensional dynamics. So it's one-dimensional endomorphism of the interval. And this goes back to the result of Tchaikovsky, and this is in fact the result for continuous systems, which nowadays is known with the popularized name of period 3 implied chaos. Period 3 implies positive entropy. Of course, the result of Tchaikovsky is much more standard. I give an order on periodic points. But in the case for endos with zero entropy, basically say that all the periodic orbits are power of 2. So it means 1, 2, 4, 8, 16. And also there is a forcing structure. So you have a periodic point or periodic orbit of power 2 to the n, then you have periodic point of power 2 to the n with n smaller than n. In the case of smooth endomorphisms in the boundary of zero entropy, this goes back to the work of Collet-Treser and Feigenbaum. They're saying that this system that they are in the boundary of zero entropy, they are infinitely renormalizable. So in few words, there is a system, a sequence of intervals, it's nested one containing the next one, which are periodic. And the period is 2 to the n. And if you restrict to the intersection of the union of the orbit of these intervals, what you have basically is an adding machine. And the dynamics there is uniquely ergodic. Of course, well, before to say that, it's like this is much deeper what Collet and Treser prove, and in fact, it's not only this. If you have a system with this property, in fact, they are in the boundary of zero entropy. This means that you can produce this infinite perturbation in a way that you are creating entropy. So it's much, much deeper. Let's just say that this is false in the circle. This means that the structure of the homology of your manifold is going to be extremely relevant in trying to understand which is the boundary of zero entropy. It's possible to get smooth homeomorphisms without periodic point, rational rotation, that by a small perturbation, they produce positive entropy. Okay, so which is the next step? So sometimes we are like, this is something that we know, and then try to move a little bit ahead in another kind of a scenario where it's possible to say something. And from one-dimensional endomorphism, we are going to move to a smooth dissipative diffeomorphism of the disk. So what is this? You have a map from the disk to itself. Two-dimensional disk. No, I didn't say much, but this is a two-dimensional disk. The interior of the image of the disk is going to be contained on the disk. So the F with the image is a diffeomorphisms. Obviously, you can embed this on the sphere. Just put a repeller on the north pole, and then the disk is attracting. And we will assume that the Jacobian is smaller than 1. Okay, so this is the setting that we will try to say something. And there is a conjecture by Charles about the system in certain way inspired by his work on one-dimensional dynamics, that for a smooth dissipative diffuse on the disk, and keep in mind the two words, smoothness and dissipative diffuse. So you need this volume contraction property with zero entropy. Any periodic orbit has period k multiplied by 2 to the n, k is odd, with k bounded by k0. So this means, let me say it again. So you have this situation, there is a k0 that is going to bound the odd part of the period. Okay, so it's like after a factor of a bounded k0, the idea that you have the same picture that you have in one-dimensional dynamics. It's kind of same result of Sharkovsky you want. And if the system is in the boundary of zero entropy, you could say more. You have periodic point of all periods. So this means that you have a whole cascade of point of k multiplied by 2 to the n for n large. Okay? With again k bounded. So which are the examples? Well, the first is this conjecture is true for the n family. If you take B small, which is the n family, basically you have the quadratic. It's something that you can do in general. You have a one-dimensional endomorphism of the circle, of the interval, sorry, and you embed it in a two-dimensional dynamics. And if G is a quadratic family, this is the typical Enon map. And they have improved by Lyubich and Martens. And in fact, they have proved much more than that. So it really goes on the whole skin of renormalization for one-dimensional dynamics. But there is the Tresser conjecture, the one that if you go to the boundary of zero entropy, the periodic points are period of 2 multiplied maybe by an odd factor. But also there are these examples that go back to the 80s by Gambodot and Tresser, or exactly the diffeomorphism of the disk that had periodic point of period 2 to the n, and it was kind of inspiration of, of his conjecture, which basically is to build a recursively sequence of diffeomorphism that are uniform dissipative. It's nothing else than that. So you have the disk, you have a fixed point. This is your F0. And then you change the fixed point, attracting fixed point, by the subtle fixed point will have negative eigenvalues. So this means that left is changed to the right. So the same on the stable. And then the stable manifold goes to this periodic orbit of period 2. Okay? And so you repeat the same scheme. You bifurcate this attracting point in one of these saddle with negative eigenvalue. And then you have an orbit of period 4. This is the third element of the sequence. And you keep doing this. And you do infinitely many times. And you can build this example. It's going to be a sequence that is converging. And all of them is uniformly dissipative. And in the limit, you have a system that have, for each n, one periodic orbit of power of period 2 to the n. Also, you say, well, okay, but Charles talked about that maybe you have an odd factor in the beginning, maybe a number 3. And you can build an example. And you start, instead of starting with the previous bifurcation, the previous idea, you take a fixed point and an orbit of period 3 going around. So this point is a point of period 3 that is rotating around the center. It's a saddle. And then you do the same process, inserting this period 3, the previous example. And then you have point of period 3 2 to the n, we need any n larger than or equal than 0. Okay. They already knew that this thesis conjecture is going to be false without the dissipation, because in fact, you can build zero entropy diffeomorphisms exhibiting periodic orbit with period 3 to the n, and it's the same idea. There is a CR convergent sequence where each Fn had period 3 to the n with any n smaller than or equal than n, and you start with the same. You produce a periodic orbit of period 3, and inside there, you insert the same, and you keep doing this, and you produce this cascade, but then you have periodic point of period 3 to the n. What happened with this example, that this sequence cannot be built uniformly dissipative, at least in the C2 topology. C0, it can be done. The sequence is going to converge. But if you want to do in the CR topology, this happens that the rate of dissipation goes to 1. So in fact, the tracer conjectures say that there's no way to do it dissipative. And there is just a remark that we will use later, that you want to start to put or to place orbit of period 3, you have to keep rotating, and then you have to bend a lot their stable manifolds. It's just a remark. Then maybe you try to do the drawing, you will realize that this happened. And this in certain way it will be a key on the proof of the conjecture. So okay, let's go to try to see if we can prove this conjecture, but we will focus with a particular class of surface diffeomorphisms, which are C1 plus delta, and we call it strong dissipative. Let me say what's meant to be a strong dissipative. It's not necessarily that the Jacobian is small, something else. So you have this C1 dissipative diffeomorphism of the disk. Any ergodic measure is going to have a negative Lyapunov exponent. Well, because basically the sum of the Lyapunov exponents is the logarithm of the rate of dissipation. And if this is smaller than 0, at least one, they have to be smaller than 0. And if your ergodic measure is not supporting an attractive periodic point, almost every point related to this measure has an unstable manifold. This comes from Pezin theory, non-uniform hyperbolic theory. And being strong dissipative means only that a stable manifold separates the disk. This means that if you have an unstable manifold, they disconnect the disk. This is the property of being a strong dissipative. So there are examples that this doesn't happen, but they are not generic. It's only one construction, and you can do it with. And in fact, the question that we are wondering if it's true that any CR generic dissipative diffuse is a strong dissipative. We don't know. What can we say about this system? This system has a particularly nice property that the periodic points are going to be dense. And this is not a perturbative argument. If they give you a strong dissipative diffeomorphisms, periodic points are dense. Where? Let's go back to the general equation about the closing lemma, CR closing lemma. It's known C1, but here we want to say something else. There is a result back from the 80s by Lai and Yan that basically says that if you have an endomorphism of the interval, periodic points are dense on the recurrent set. And it's not perturbative, this happens. For the two-dimensional this strong dissipative diffeomorphism of the disk, this is a recent result by Sylvain Crovisier and myself that says that the periodic points are dense on the closure of the support of any measure. You take any measure, you take the closure of the support, periodic points are dense over there. It's just, it's coming from the fact that you have this stable manifold separating the disk and some kind of topological observation that is going to force that you have a lot of periodic points. So why we only know that it's on support of the measure? Because we are using strongly the property that you have stable manifold separates, but the stable manifold are defined on these ergodic measures. This result starts to say something about the conjecture of Charles, basically the following. If you have a system that is in the boundary of zero entropy, this is strong dissipative diffeomorphisms, you have to have infinitely many periodic orbits. Why? Because if you prove, so if all your ergodic measures are only supported on periodic trajectories, you can prove, under the hypothesis of strong dissipativeness, you are in the interior of entropy 0. And therefore, you have to have a measure which is not supported on periodic points. So it means a non-periodic measure. But the periodic points are dense. So this means that they are periodic point approximated. And you have to have infinitely many of them with period going to infinity. Otherwise, your measure is periodic. So this is something to say, OK, so if you are in the boundary of entropy 0, you have to have a lot of periodic points. This result is relevant whenever there is a 0 Lyapunov exponent. Of course, there is this result by Katok that says if you have one negative Lyapunov exponent, one positive, periodic points are dense. So this is for hyperbolic measure. But for some reason, the Lyapunov exponent is 0, and this is the case when you have 0 entropy. You don't have this unstable or this repelling let's say, well, positive Lyapunov exponent that help you to build the periodic points. You have one 0 Lyapunov exponent and one negative. And then you have to go to this result. And so if we want to understand the system that is in the boundary of 0 entropy, we need this type of result. OK, but let me say a little bit more. We will put another condition, 9/10. 9/10. It looks like arbitrary, and this is the condition. And I will explain this, what this meaning. It means that the Jacobian is smaller than the minimal norm power 9/10. Basically, it says if you want to say something, if you have two Lyapunov exponents, the positive one, if there exists, is not too large. Because, well, the Jacobian is the product, the minimal norm is the smallest, let's say, but then it's for different points. It's a kind of uniform property. And so basically saying that the largest Lyapunov exponent is not too big, which is OK. You have in the boundary of entropy 0, because the measure that are not supporting periodic point have to have 0 Lyapunov exponent. But why we wonder about this? Why we put this condition? Of the moment it's a technical, I will explain why is the reason. OK, so which is the main property of this condition are the following. The first one, that this 9/10 strong dissipative system is an open property. In general, when you want something dynamic, you give a condition. It will be great, it's an open condition. Otherwise, you say, well, it will be meager. So this means that if your system is 9/10 strong dissipative, any one nearby is also 9/10 strong dissipative. And the second one, maybe it's much more interesting, which is satisfied. So this condition is satisfied by two-dimensional diffeomorphism near a one-dimensional endo. So you have these endomorphisms, and you pick up a two-dimensional diffeo with this structure, and you pick up this B smaller than 1, small. This system is strong dissipative. So there is a large interesting class in itself. They have this property, and because it's open, it's not only this type of contraction, but also perturbation of these guys. Okay? So, and the reason why this two result follows is basically because the 9/10 condition implies a kind of uniform Pezin theory. Yeah, well, because it's an open property. The 9/10 strong dissipative. Yeah, because it's 9/10 strong dissipativeness is an open property. Yeah. It's not only that they satisfy this condition, but the fact that the stable manifold are going to separate both. And the reason that we are dealing with this is because we want some kind of uniform Pezin theory. It's something that is kind of, what is the meaning? Pezin theory for non-uniform dynamic, and you talk about uniform. So what is this? So let's go back to Pezin theory. Basically say that if you have a measure, there is what we call these hyperbolic blocks, where the Lyapunov exponent, at least the one that they are different than 0, they have some kind of uniform contraction. you have a stable manifold, and in this hyperbolic block, from point to point, the stable manifold moves continuously. It's not in the whole set. So maybe there is a set of positive measures that there the stable manifold forms a igual lamination. Okay? And what we want is that, in fact, if you take all your measures, so you take all the measures, always there is a hyperbolic block with some kind of positive weight, that you take the union all of them and the closure, still the stable manifold forms a one lamination. It's basically this. It's only technical condition, and maybe we don't need it. Maybe this 19 condition is not necessary to get the result. This has been observed on the literature in the work of Benedict Carlson appear, in the work of Jean-Christophe, in the work of Pierre also is appearing in a certain way, because you need kind of two conditions, some kind of uniform contraction on the Lyapunov exponent and some kind of domination property. It's only just an observation. But maybe it's not necessarily. So by the moment, we need it. So let's go back to the conjecture and see what we can prove in this universe. No? So from now on, it's a strong dissipative diffeomorphisms, C1 plus delta, with this 19 condition, and zero entropy. So the conjecture of Tresser is true. So this is the result, the first one. Again, just to remind it, it's like there exists this K0, such that whatever periodic point that you have, they have period K multiplied by 2 to the n with this K bounded. And also they have the forcing property. So you have some periodic point with period K to the n, then you have the lower ones on n, means K to 2 to the m. So the K you have to keep it. And this K0, this related to the proofs, is going to depend on the rate of dissipation and the CR norm. In fact, if your rate of dissipation is allowed to go to 1, this K0 starts to increase. And it's something they have already observed on the Denon family, but basically it's, well, we will see why it is related to the rate of dissipation. Okay. You say, well, if I iterate, so there is a property of this 910 diffeomorphism, strong dissipative. If you iterate it, you improve the 910 condition. But, well, the norm could explode. And so maybe this K0 does not necessarily improve by iteration. But maybe yes, it can be discussed later. Okay, which is the theorem B? It's about the boundary of zero entropy. Of course, the thesis holds, because if you are in the zero boundary, you are also zero entropy. But you have a full cascade. This means that you have periodic orbit with period K1 to the n with some K1 bounded. Not all K1 below to K0. There is a K1 that is bounded by this K0, and you have like all these periodic points. Infinitely many. So basically, it's like the conjecture of Tresser says, and the result says, that you can recover kind of the one-dimensional result up to this K factor. Is the converse true? What does it mean, the converse? In the one-dimensional case, if you have the property that the periodic point goes to infinity, then you can perturb to produce positive entropy. Or the period goes to infinity, you can perturb to produce positive entropy. Here we don't know. So you start with a guy that they have infinitely many periodic points with period on this type. Can you perturb in a way to produce positive entropy? So C1, you can do it. There's no problem. CR, let's go on the rigidity problems. And in the one-dimensional theory, everything is built up around the critical point. As you know, for two-dimensional diffeo, there are no critical points. And so it's not clear where you have, which is going to be your lever. And here is like the lever is going to be the structure of periodic points. But maybe it's true, I don't know. But this goes in the scheme of renormalization. And which is the theorem C? The theorem C is yes, your system is topologically renormalizable. It's not like a rigid, smooth renormalization, it's just a topological. There is an instant sequence open set, which are periodic with this factor k to 2 to the n, and you have the intersection of the union of the orbit of this open set. In the closure, the dynamics is uniquely ergodic, and is measured equivalent to an Edding machine. So you have kind of similar result. So for instance, in the 910, the measures, so clearly the Lyapunov exponent is 0, but uniformly you converge. So in this set, the 910 condition gets improved as much as you can. And so maybe the 910 condition in general is not necessarily, but okay. Let's try to go to the proof, and let's go first with one observation, the one-dimensional proof. The proof rely on one-dimensional dynamics that there is an order on the line. So what is the total order? If you take a point disconnect the line, and giving 3 points, one separate the other two. So it's like this. No, you have 3 points, at least one is separating the other two in different connected components. And in fact, if you just do observation, this is enough to prove that period 3 implies chaos. You have a point of period 3, and then you rely on this observation. You will realize that this is enough to produce. And we will go through this proof in the two-dimensional case, that this is enough to produce chaos. Which is the two-dimensional counterpart? Obviously, one point does not separate the disk, but we use the stable manifolds. Stable manifolds separate the disk. And this is where the strong dissipativeness gains came back, showing that the hypothesis of strong dissipativeness is like the stable manifold separate the disk. Okay, but you don't have this total order. In fact, you have 3 local stable manifolds. It could hold that no one separates the other two. The other way is when that order is by rotation. So we don't have this total order structure. So what we do? And in fact, if you have a point of period 3, this is what to happen in certain way. This is a structure that have to happen if you have a point of period 3. They have to go around. Because otherwise, you are going to produce positive entropy. Anyhow, let's define this object with a totally orderly subsequence. You take an orbit, a saddle orbit, the saddle periodic orbit, of period D in this case. We say that a subset is totally ordered, so we are already going into the proof. It's totally ordered. If you pick up any 3 points, the stable manifold of 1 point separates the other two. So okay, so here you have a period 6, but then you can pick up these 4 points, and their stable manifold are totally ordered. No? So you are like 1 separating another 2, etc. So you are removing this one, and the one on the top. You only keep this one. So this is a subsequent is totally ordered. We introduce this quantity. NOP is the maximal cardinality of a totally ordered subsequence. In this case, it's 4. And the proofs go to understanding this number. So let's give an example. On the left, this is the string cases. So again, I repeat the same. This is a sequence with totally ordered. And here, the only totally ordered are 2 points. And this is what we call they are fully decorated. The whole orbit is decorating the disk. They're moving around doing this decoration. And this is one, the totally ordered subsequent is 4, in this case is 2. There are 2 string cases. With a totally disordered, non-well-ordered subsequence is the extremal case where everything is going around. The number n is always 2. So what are the 2 key theorems that prove that, the conjecture? One is related to the zero entropy, so how zero entropy gives an upper bound on this number. So this is the first result. So we are going to, given any orbit, we are going to bound this number. And so if you have zero entropy, if you have a periodic orbit of period D, the maximum subsequent is totally ordered is smaller than or equal than 2 to the L, where L is the number of divisors of D counted with multiplicity. Okay, so there is some kind that is coming from zero entropy. They have a certain combinatorial structure that, for instance, you have a period phi, NOP is going to be 2. The divisor is going to be 1 and 5. Any prime number has this property. Okay, so you have this, the zero entropy gives upper bound. From now on, I repeat, everything is 9, 10 strong dissipative on the disk, okay? So it's under this hypothesis. And the second one is like the dissipativeness give a lower bound on NOP. And means that there exists an alpha, and this alpha depends on F, and in fact on the rate of dissipation. And what happened that the cardinality of the maximal totally ordered subsequent divided by the period is always larger than alpha. So this means that it's very frequent, you have to have this total order if you assume dissipativeness. Okay, if you assume these two theorems, you prove the result. So the theorem 1 and 2 imply theorem name. Remember, we want to find this K0 such that you bound uniformly the period of all periodic orbit, the odd part. So you take a periodic orbit of period D, K to 2 to the M. K is the odd part. On one side, N of the maximal totally ordered subsequent have cardinality divided by the period have the cardinality of the you know it. The cardinality of the totally ordered subsequent divided by the period have to be larger than alpha. This is coming from the dissipativeness. And on the other side, it has to be smaller by 2 L prime 2 to the M. But now L prime is just the number of divisors of the prime part. And the period is K to the N, so it's 2 to the L prime divided by K. Okay? Now remember that we say that, just to make it clear, that NOP is smaller than 2 to the L, but L is divisor of L is the quantity of divisors of period counted with multiplicity, but if you write the period of K 2 to the M, the multiplicity of 2 is M, and then you have to analyze what happened on K. But now it's done. So if 2L prime divided by K have to be larger than alpha, and alpha depends on the system, not on the orbit, K has to be bounded. And that's it. Now, because let's assume that it's a prime number if you want. It's like, well, K cannot go to infinity. Because on the top you have, and then you say, no, but it have many, but it's odd. So in the worst case, all the divisors are 3, 5, blah, blah, blah. Okay, but on the top you have 2, and on the bottom, in the worst case, is 3 power to the L prime. 2 divided by 3, L prime is larger than alpha, and then you bound it. Just an observation. So everything boils down to this formula, to this relation. So, okay, so we have to prove this two theorem. And the proof is the first one, we want to bound the upper bound of N. And remember, we want to bound NOP more than 2 to the L, where L is the number of divisors of D counted with multiplicity. And the heuristic is provided by the example. Really, the example gives you the road of the proof. Well, you have to show that actually these examples are what really is going on. And what is here, this is the example that was 3, 3, 3, 3. I just stopped like it. You have a point, fixed point, a point of period 3, and then a point of period 9. They have this decorated structure. And then if you want 27, etc. going around this. Or you have the other one that looks like a period doubling. So what happened in the proof, that the periodic orbits are organized as in this example. So there is a kind of filtration on periodic points that's going to look like this. Let's try to show. So there is the zero entropy is going to force the structure of periodic orbits. It's a kind of filtration. And you see that if you want to get the totally ordered sequence, at least, at most, in each component, you can choose two stable manifolds. Here you can choose all of them. So there is one component of this filtration, another one here, here. But there, you want to be totally ordered, they have to be like parallel, these stable manifolds. But for here, you have to remove this one or this one, and then you keep this, and you keep the one on the top, and then you go to 3. So this idea is like the organization on this filtration force that you want to get this totally ordered sequence. Basically, you have to choose a stable manifold that looks parallel, and therefore this produces that you are coming down the quantity that you can choose. Let's prove it. So let's start with the definition, which is a separating set. Let's try to show why this could be true. It is an heuristic. Let's start saying, what is a separating set? Separating set is a collection of connected sets with boundaries. Okay? So Z is a collection of connected sets with boundaries. And the boundary is given by local stable manifold of saddles with period dividing D. D is the quantity of its set. And arcs in the boundary of the disk. This is one example. So here you have Z has 6 connected components. 1, 2, 3, 4, 5, 6. And the orbit here, so these are a stable manifold of periodic points. Some are going to be fixed, some are having period 3, and some are period 6. This is separating set. Just a definition. And you can talk about, of course, this number with the maximal number of totally ordered components. And being totally ordered means that the boundaries are totally ordered. Here we have this 1, 2, 3, or 1, 2, 3, or 1, 2, 3, 1, 2, 3. 3 is the maximum. Okay? Just the same definition, but look into this separating set. Okay. And now we say that two of these separated sets are nested. The first condition is you have CD prime and CD, D prime divided D. So, and the connected component of CD are contained in the connected component of CD prime. Each component of CD prime contains exactly D divided by D prime of CD. Each component of CD prime contains D divided by D prime components of CD. And inside of the component of CD prime, the component of the next one are all decorated. This looks like complicated, but there is a clear structure. Think about filtration. So here you have CD prime, and here it will be C3, 3 components. No? And then you put the next one, and then you put 9. So 3 have to divide in 9, could be 6. But in each one you put 9 divided by 3. 3, 3, 3. So this is going to be CD, and the other one is CD prime. And they are decorated. So they have this structure. This means that they are not ordered in a certain way. So you have to be like, so this means that you look inside here, the maximum cardinality of components that they are ordered is only 2. This with this, this with this, here this one, etc. So this is the definition. And what happened that we say that the periodic orbit is partially decorated, you can get this sequence of nested separating sets. And each connected component of CK contains the last one. So you have C0, C1, C2. C1 refines C0, C2 refines C2, C3 refines C, etc. And the last one is the last refination. And each component of the last one contains only one iterate of P, of the orbit of P. And the main lemma is like each periodic orbit is partially decorated. You believe this lemma, you prove the result using this structure. Later, we give an idea why the lemma. Here we have an orbit of period 12. So the first element of the filtration is the whole disk. Then you have a filtration of 4. So 4 have to divide 12. And inside there, so this is the component of the next element of the filtration, C1. C1 has 4 elements. And in each one, you have to introduce a new one. And so you introduce the 3 that separates inside there. So this will be an example of what is this sequence of nested separating sets or filtration. If you believe this, you can prove that the main lemma gives the upper bound of NOP. And exactly, this is like what I said, they were kind of following the examples. If you want to build this example, the Treser, Gambodó, and Van String were proposing, basically you are doing that. And what happened first, so let's say how the main lemma gives the upper bound. You have the filtration, which was the property, each element, each separating set has dj components. And in each component of Cj, you produce this quotient, decorated component of the next one. Oh? So here it was 1, 4, 12. And so 12 divided by 4 is 3. So you put 3 elements on the previous one. And that's it. It's very combinatorial. The quantity of totally ordered component of this guy is smaller than 2 divided by this. So assume that you have this number. In each one of these elements separated set, if you want to produce total order, you only can choose 2. You cannot produce 3 because they are decorated. So remember that this decoration is the opposite of total order. Now just to say it, well, you have over there the picture. So you have these 3 elements. You have, assume that on the last one you have whatever number. In each new component you have to choose at most 2, because they are going around this way inside the component, and you want them to be parallel. So you have this. And by induction, well, first, the orbits in the end, imagine that it's a saddle. The total order is always smaller than the last one. And by induction, this is smaller than 2 to the k. The quantity of element of your filtration, or separating set of your filtration. But the number is smaller than 2 to the L. Why? Because the number of elements of each separating set have this division property. And the last one have exactly d, which is the period of the orbit. So how many of these components you can put, or sorry, separating set at most, L, which is the number of divisor of d. It's just a combinatorial observation. And that's it. So we have to believe the main lemma, and let me give an example why this main lemma could be true. And just let me think only a little bit about periodic orbits that have odd period. And this goes down to the first, this result by Cartwright and Littlewood, which basically say that you have an invariant continuous set that does not separate the planes, always have a fixed point over there. Well, you have a continuous set which is invariant for homeomorphisms, you have to have. Does not separate the planes, you are not producing something like look a Jordan curve. Well, it's really like you have the plane and the disk, just a continuous set, who knows. Always there is, and it's invariant by f, then there is a fixed point there. If it's periodic, you're going to have a periodic point there. Which is the Leschetz formula. It tells you basically which is the relation of number of periodic points related to the homology of your disk, and you can consider on the sphere. And these two things imply that if they are not homoclinic intersection, there are no homoclinic intersection between saddles, because otherwise you have positive entropy, and you look odd period, always exists orbits such that they are unstable manifold accumulate on periodic point of lower period. You can reproduce this argument on dimension 1 if you want. Why is this the last one? Because, for instance, the left-hand formula says that the number of periodic points of index 1 and this is index minus 1 are the same. And if you have the previous, and then you produce the number of connected components. I go into the proof, and believe me, this one is very straightforward. You just go back to the 50, so I don't say anything new. So the first line is something goes back to the 50. So what happened, now you have an orbit with odd period, the unstable branch accumulates on other with lower period. So you have the unstable branch, go in there. But this has period 3, let's assume. So the next iterate has to be over there, it cannot be here. Because you go here, you have an homoclinic intersection. Because one is iterate of the other. So you have to go to the other side. And the next iterate cannot be neither there or there, so it has to be there. So start to decorate the disk. So this is like if you have period 3, odd period, you have to be rotating around the center. And if you want to do the same picture, but inside the connected component, here you have an orbit of period. This is period 3, this one. And this other is period 9. So this orbit has period 9. I put only 3, but we'll see this is stable and this is unstable, and stable go here. The next iterate has to be, if you take an iterate by 3, it has to be over there, the same over there, the same over there, and the next one here. And then you have this decoration structure. If you want to avoid this homoclinic intersection, you have to start to be going around this way inside this connected component, and you have this decoration structure. So the first, and this is we bring in the next separating set. Okay? So in certain way, this zero entropy force this decoration, and therefore this structure on periodic orbits. Good. So this is a kind of flavor of how this build up. If you have zero entropy, the structure of periodic point have to be like that. So what happened with the lower bound? And this related to the dissipativeness. So the goal is to have this property, that there exists this alpha, that the number of totally ordered subsequence divided by period is larger than alpha. And this is exactly this. There exists beta such that for any ergodic measure mu, there is a set of positive measures larger than or equal than beta, such that all the local stable manifolds, the point in the union of these hyperbolic blocks, form a C1 lamination. It's not in the whole set, just you take the hyperbolic block, you take the union, then you have C1 lamination. But you have C1 lamination, stable manifolds start to look parallel. They are ordered. And the weight, this is a beta uniform, the weight, so this means that this property of being parallel of the measure is a fixed proportion for stable manifolds. For a fixed proportion, the local stable manifolds are parallel, and in particular, they hold for periodic measure, because it's for all the measures. So in particular, for periodic measure. So now for periodic measure, you have that this stable manifold like this, and they start to look parallel. So with a big proportion, if you have this parallel property of stable manifolds, you have the lower bound, so a fixed proportion of the lower bound on the total decoration subsequence. Okay, so you have the two elements, and let's start to give how from there you build the renormalization structure. On one-dimensional dynamic, the lever is your critical point. You build everything around your critical point. Well, here you cannot build on critical point. In principle, you don't. In principle, there is not a candidate of critical point. So what you are going to use is the structure of periodic point to organize the filtration. Okay, so you use the structure of periodic point that are forced by zero entropy, and this shows that you have to produce the renormalization, the topological renormalization scheme. This means that you have this nested sequence, that this disk after k to 2 to the n are sent properly inside, and inside there another one, etc. Okay, so we have the theorem. So you use this theorem to revisit the filtration that we build of the nested separating set. What we know is basically in each component, now they appear the factor 2, let me say for j large. In each component Cj, there are 2 components Cj plus 1. Why? Because otherwise you have this huge drop on the totally ordered set sequence and you cannot have it. And the property also is that this separated component have the property that a stable manifold goes inside. Maybe go to the next one, but it now goes down. So you have this order, and the stable go inside, but does not go down. So it's a kind of you have what is called the Smale order of periodic point. This filtration of a periodic point gives this, is coherent with this Smale filtration on periodic point, a Smale order on periodic point. So this means that, let's say this. So for instance, you take this periodic point, you have 2 components. Later you have this periodic point of period 2. Now you have 4 components. So then you have this periodic orbit of period 4, and you have 8 components. And a stable manifold have to go inside. So they can go, they remain inside this one, but can go to the next one, etc. I just here repeating the drawing of what's going on for the example of period doubling. But this is kind of prototype. The other way that this filtration can be built is using this. You have this fixed point, and then you have this saddle jumping around this. And so this unstable manifold from here goes to there. So it's looked like previously. And your first connected component of this. The next one is on this point of period 2. Now there is a point of period 4 going around, decorated around. Remember now everything is 2. And now you have these 2 components, and a stable going to the next one. But in fact, there is only 2 ways of creating new separating sets, like the period doubling saddle of the 2 decoration. This is the only way that you build. You build a new separating set either introducing a periodic point with negative eigenvalues, or you introduce it a periodic point that's going around of one of lower period. In one-dimensional dynamics, this basically looks like the period doubling, or this something that does not happen when you have a negative Schwarzenberg derivative. People that is, how do you say that is, knows a little bit of one-dimensional dynamics. So this will be the period doubling. But then you can have something like that. Here is like and this will be the point of period 2, that then stable is going to this fixed point. This cannot happen if you have negative Schwarzenberg derivative, but here there's no obstruction, and then you have this structure. There are the 2 ways that you generate this separating set. And this structure is one that gives the attracting regions. So this is what we are looking, attracting regions. How you build this attracting region? So look into this way, the period doubling or 2 decorations. Period doubling is saddled with negative eigenvalues. Assume that you have this fixed point, that they have negative eigenvalues, chum chum, or they go to a point of period 2. And then assume that there is another unstable manifold accumulating here. Because this area jumps to the other side, the unstable manifold has to cross. And if you are here now, you have to go back there, and then start to produce an attracting region. It's a little bit more complicated, but this is the way that you use to produce attracting regions. And this is classical in one dimension in a certain way. It's embedded in the picture. With 2 decoration, you have the same. You have kind of the similar. You have now, it looks like the same, because if you collapse these 2 points, you have this picture. So this is fixed, and this is period 2, plum, plum. And then a stable manifold accumulates this guy, because this part goes to there, then a stable manifold have to cross, and from here go to there, and then you produce attracting region. So this is the way one element of you produce an attracting region. And what happened, that you are going to choose attracting region that intersect infinitely many separating sets. So this produces that if you have an attracting region and you are having separating set, and the only way to produce separating set is through this mechanism, you produce inside there another attracting region. And then you produce the scheme of the period region, that they are the periodic region that is going to be attracting, and this gives the renormalization, the topological renormalization. Okay, this is really maybe some idea of the proof. Maybe it's neither a flavor, but something is a kind of combinatorial structure. So what else? Merci, Jean-Christophe, and Sylvain came up with a really nice picture. I think that he got the feeling of the positive message of Jean-Christophe, exactly this. So this kind of decoration set are in certain type of puzzle. So that's it.